All right, so we left off with this example, and it's similar to what was in the video, but it doesn't hurt to work back through it. So we left off talking about taking this alkane, 2-methyl pentane, and doing radical substitution on it. All right, so this is different from our other pentane that we used up top, because basically everything here is abstractable, right? The only two equivalent sites are the two primary sites that are highlighted out here, right? But everything else is going to be abstracted. So you're going to get more products, which we have shown over here. We named them all to show that they were all constitutional isomers, which have the same molecular formula but a different structure. And so now we're going to talk about how we got there. So we know the what, and now we're going to do the how. All right, so let me put a date on here. What's the date? Dang, it's October already. Wow. So now we're going to talk about the mechanism. So obviously, right, there's an initiation step. What happens in that step? You should be able to converse with me on this on some level at this point. What happens in the initiation step?
Do you create the radicals?
So the chlorine is my initiator. I'm going to shine light on it and basically break it in half homolytically. Is that right?
Yes.
My new is not, it just ain't kicking. There we go. That's worse, but it'll do. So this is homolytic bond cleavage. Is that right? So this is going here and here, like so. It doesn't matter if you put it on the top or the bottom. All right. So that's my initiation step. Right. So all of the chlorines that I make up here, right, all of the chlorine molecules that get chopped homolytically, right, I can use those in my propagation step. Now this is going to be a little more involved, just because of the fact that you got so many carbons where you can abstract from. What happens in propagation?
Abstraction?
Mm-hmm. So new radicals form through abstraction. All right, so new radicals are formed through abstraction. And with this chain, which I'm going to steal from up here, every one of these carbons is abstractable. The only one that's not going to get abstracted, not that it won't, but that we don't need to show that, is going to be the real thing. The primary is on the end. So I'm going to take the highlights off, but I'm going to leave the colors though. All right. So where do you want to start? You want to start, and I'm going to put in, it's going to take forever if I make them the same color, but I'll put the hydrogens in that we're going to take off. Right, so all of these, and then I'm only going to show one of these down here, because again, we're only concerned about one, even though they're both abstractable. We only need to show one, all right? Because whether you abstract from the top or the bottom, we already showed through naming it that you'll get the exact same compound. All right, everybody okay with that?
Yes.
Where do you want to start? I need to shrink this, it's too big. All right, where do you want to start? You want to start on the far end? Or you want to start at the branch? How you want to do it? Doesn't matter.
It doesn't matter.
All right.
And
I'm
so
gonna start on, I'll start on the far end with the brown, the carbon that's highlighted in brown. So this is plus. Chlorine. Come on, electrons, do right. All right, so plus that, and again, I'm gonna just show this hydrogen coming off. I'm gonna make that bond longer so we can show the arrows. All right, so it's always here, here, and here. Is that right? That's how we show abstraction. It's normally shown using 3 arrows, right? An arrow from the radical initiator, and then you show the bond where the hydrogen is coming from. You show that bond breaking homolytically. All right, so now that's that. That's going to give me a new radical, and I'm going to just paste this again. I don't feel like drawing it. All right, so it's going to be here. Like that. Everybody agree? Plus HCl. Anybody not see that, or anybody disagree with that? All right. So now we're just gonna walk the chain. Let's do that. All right, take that secondary that's highlighted in yellow, and we're gonna abstract from that site. Right, and I just want to show again that bond breaking. I'm gonna do an arrow like that instead. And
Thank you. No, thank you.
all right. Oh, let me put that back. All right. So that's that. We're breaking that CH bond. And then I'm just going to, I can steal this. Right, I'm gonna put my radical right there, plus HCl. Keep in mind that hydrogen, that second hydrogen is still in place, whether I draw it in or not. Sometimes you'll see it drawn in, sometimes you'll see it left off, but it's still there, right? It doesn't just disappear. Add a page in so we can,
what do you mean?
this hydrogen right here.
Okay.
Yeah, sometimes you'll see that showing, sometimes you'll see it not showing. If it's not showing, it's still there, right? Unless there's some type of charge on that carbon, that other hydrogen is there, all right? But I'm leaving it in just for the sake of clarity. All right, so we're gonna take now, in the third propagation step, we're gonna take these hydrogens down here. Uh-oh. So that plus chlorine radical. right? And I'm going to show again the homolysis of this bond. And then chlorine is facilitating that. So I need to show chlorine donating 1 electron this way. Right, if you notice, nothing really changes. Like it's the exact same pattern of electron flow when you break the CH bond and then when you're making the HCl bond, right? It's the same electron flow for propagation. So now that's going to give me this. I'll draw the other hydrogen in. That's there. And I got a radical right there, plus HCl. Anybody not following? Let me fix that. I don't know where that came from.
We'll pretty much just end up writing it for each different degree, like each one on there.
Yep.
Okay.
Yep, because all the carbons are different except for those 2 on that branch. You got to show every propagation step. All right, so that's that one. And then we got 2 more. All right, so we have a hydrogen here at the tertiary site. And notice I'm not doing this all on the same molecule either. Every time I do a propagation step, it's on a new molecule, right? Because once I make a radical on one of those molecules, I can't go back and pull off another hydrogen and make another radical in the same molecule, right? This is happening on different molecules of 2-methylpentane. Right, so that's that plus chlorine. This doesn't change, same arrow, same everything, just a different location. So I'm gonna draw that like that. I'll draw the other arrow back to carbon, all single-headed, and then I'm just gonna loop this around like that. That's really bad to do that. Could have put the chlorine on the other side, but you got it. So then I'm gonna get this radical. Erase that. I'll get a radical right here. Right, and since that's tertiary now, there's only 1 hydrogen there. So don't lose that. Don't think you got to draw another hydrogen in because you don't. It's a tertiary carbon, so it's only going to have 1 hydrogen anyway. All right, everybody okay? And then I need to do the last one, which is the top one. And I think I made that, yes, on the bottom. So show that like that. Same exact thing is going to happen, just at a different location.
I have a question.
Go ahead.
Could you do the primary carbon at the top?
Yeah, I said that earlier. You can do either one, but you're going to get the same product. So we just pick one. We see how right here, these 2 products where 1 chlorine is on the bottom right here, and then I got 1 on the top, but when you name it, it's the exact same thing. Yeah, so we just picked one. So I just picked the bottom one.
Okay.
But both are equally susceptible to abstraction. Yes. Right, so let's go back to here. We're just gonna pluck this off same way. Nothing changes. If you notice, all the arrows are the same, right? Nothing changes. Homolytic cleavage of the CH bond, and then the chlorine is making a bond with hydrogen. So paste that there. And It's now a CH2 with a radical there, plus, ooh, made the arrow too long. That's all right. All right, so that's that. Those are all 5 propagation steps. All right, and notice the arrows look the same. I'm breaking the CH bond homolytically, and then I'm donating 1 electron from chlorine to hydrogen. All right, and that doesn't change. It doesn't matter if you got 1,000 carbons. That propagation is always going to look the same. If you're doing abstraction, it's always going to look the same. All right. So now we just need to do, actually, you know what? We got time. I'm gonna let y'all do the termination, or try to do it anyway. So let me zoom out so y'all can get a good. 1, 2, 3, that's all 5. You can see all 5 radicals. If you don't have them written down, you can. How many people we got today? 30. Breakout rooms. All right, so I'm going to open up breakout rooms. We're going to take 10 minutes. I want y'all to do the termination and work together, talk it out. Don't be in there on mute. I'm going to pop in anyway, but we're going to take 10 minutes. And I want you to walk through, take all 5 of those radicals and terminate them with chlorine. All right, and those who are away from your device, and you just logged in, if you're not in the waiting room, I mean, you're not in the breakout room, then I'm putting you in the waiting room. There's no, you can't hang out here with me. You got to go in a breakout room. So make sure you go to your assigned breakout room. All right, we got 12 people that haven't joined, 11 now. All right, go ahead and join a breakout room. We got 10 minutes to work through this termination. Still got 8 people need to join. All right, so we have the sum at the bottom. We picked out from our molecule, because we're calculating the product distribution. We picked out that there are 9 primaries, 4 secondaries, and 1 tertiary. So now we're just doing the sum. So that's going to be 14.2 and 15.6 is 29.8.
Yes.
$29.8. All right. So now it's just a matter of applying the equation. So if we want to figure out how much of each product we're going to get, we can apply the equation for each one. So let's do the tertiary one first. So tertiary is 1 times 5.2 in the top divided by 29.8 times 100. This is a tertiary, the tertiary product. Help me out with the calculation. It's going to be somewhere about 11 or 12%, somewhere like that. Anybody got it?
We're at 17.4.
17.4%.
Yeah, that's what I got as well.
Okay, all right, that's fine. That's about, yeah, that's about right. That's about right. All right, let's do the secondary, but let's do them separately, right? So for one of those secondaries, let's say for this one, we're gonna call it secondary A. And then for this one, we'll call it secondary B. So let's do secondary A, right? At that site, the N is going to be, and add another page, shows. At that site, the N is going to be 2. So that's going to be at the top for secondary A, 2 times 3.9 divided by 29.8. What do you have? 7.8 divided by 29.8. It's gonna be somewhere in the 20s.
I got 26.17, 26.2.
All right, let's keep the same number, sig figs, 26.2%, 17.4%. And then for secondary B, it's gonna be the same number because it's only two hydrogens at that site as well. So it's gonna be 26.2%. Are y'all following that? And then for the primary, we're gonna have to have a primary A and a primary B too, because you got 2 primary products. This we'll call this one primary A. And then the other primary down here, we'll call it primary B. All right. So with the primary A, that's three hydrogens that will be at that site where that chlorine is. So we're going to put that in the top. So it's going to be 3 times 1 divided by 29.8 times 100. And I'll clean that up before I post it. What do you got? About 10%, somewhere up in there, 9,
Yes.
10.1.
10.1. And then for the other one, primary B, and when I post the notes, I'm gonna put the products next to this so you'll know what I'm talking about. For primary B, it's gonna be 6 because it's two carbons. Remember that? So you got a carbon here and a carbon here, and they're both CH3s. So that's 6 times 1 over 29.8. So it's gonna be close to 20%, I think, something like that. Times 100. What do you got?
20.1,
Is it 20.1?
yes.
Right, and remember, everything has to add up to 100. Right, so 17.4, 26.2, were really 52.4, and then 10%, 10.1 and 20.1. So it has to add up to 100.
It equals 100 exactly.
All right, perfect. So we did all the mechanism, all the steps, and we showed the product distribution for each product, right? So we got to stop here. We're about 4 minutes over time. I'm going to clean these notes up before I post them. And then I'll also post the recording to YouTube